Setting alarm limits in vibration analysis based on ISO 10816, ensuring reliable machinery monitoring and fault detection. Setting alarm limits in vibration analysis, presentation overview, vibration monitoring basics, why alarm limits are needed, ISO 10816 overview, ISO 10816 severity zones, ISO 10816 severity chart, how to interpret the chart, setting alarm limits, practical engineering example, common mistakes to avoid, key takeaways. This slide introduces the engineering context of setting alarm limits in vibration analysis, emphasizing its importance in condition-based maintenance and asset reliability programs. Vibration monitoring is one of the most widely used techniques for assessing the health of rotating machinery such as motors, pumps, compressors, and turbines. Alarm limits serve as quantitative thresholds that transform raw vibration measurements into meaningful maintenance actions. Without properly defined alarm limits, vibration data alone does not provide sufficient guidance for decision-making. From an engineering perspective, alarm limits help balance machine protection, operational availability, and maintenance cost. Setting limits too low may result in frequent false alarms, unnecessary shutdowns, and reduced production efficiency, while limits set too high increase the risk of undetected faults progressing to catastrophic failures. This presentation is structured to guide engineers through the rationale, standards, and practical considerations involved in alarm limit setting. It is based on ISO 10816, a globally recognized standard that categorizes vibration severity into defined zones. The goal is to equip reliability engineers, maintenance engineers, and vibration analysts with a structured and defensible methodology for implementing alarm thresholds that are technically sound, auditable, and aligned with industry best practices. This slide outlines the structure and learning objectives of the presentation to ensure a clear and logical flow. The session begins by establishing a common understanding of vibration monitoring fundamentals and the role of alarm limits in machinery protection. It then introduces the ISO 10816 standard, which provides the technical foundation for vibration severity evaluation. Subsequent sections explain the severity zones defined by the standard and how these zones are represented graphically in the reference chart. The presentation then focuses on practical interpretation of the chart, guiding engineers through the steps required to classify machine condition based on vibration measurements, machine size, and foundation type. Attention is also given to alarm strategy development, including the distinction between alert and danger limits, and how these thresholds should be adapted based on machine criticality and operational history. Realistic engineering examples are used to bridge theory and practice. Finally, common implementation mistakes and key takeaways are discussed to reinforce correct application. By the end of the presentation, participants should be able to confidently interpret ISO 10816 charts and establish alarm limits that support safe, reliable, and cost-effective plant operation. This slide provides a foundational overview of vibration monitoring as a condition monitoring technique. Vibration monitoring is based on the principle that mechanical faults in rotating machinery generate characteristic vibration patterns. Common fault conditions such as imbalance, misalignment, looseness, bearing defects, and gear damage all produce measurable changes in vibration amplitude and frequency content. Engineers typically evaluate vibration using parameters such as displacement, velocity, and acceleration, each of which is sensitive to different fault types and machine speed ranges. ISO 10816 primarily uses vibration velocity expressed in mm/s/RMS because it provides a reliable indication of overall machine condition across a wide range of industrial equipment. Sensors such as accelerometers and velocity transducers are installed on bearing housings to capture vibration signals during operation. These signals are then processed and trended over time. Understanding these basics is critical because alarm limits are applied to measured vibration values. Without an appreciation of how vibration is generated, measured, and influenced by operating conditions, alarm limits may be misinterpreted or misapplied, reducing the effectiveness of the monitoring program. This slide explains the engineering justification for defining alarm limits in vibration analysis. Alarm limits act as decision thresholds that indicate when machine condition has deviated from normal and requires attention. In an industrial environment, maintenance resources are limited, and not every increase in vibration warrants immediate intervention. Alarm limits help prioritize actions by distinguishing between acceptable operating conditions, developing faults, and potentially dangerous situations. From a safety perspective, timely alarms reduce the risk of secondary damage, fire, or personnel injury caused by mechanical failure. From a reliability standpoint, alarm limits support planned maintenance by providing early warning, allowing repairs to be scheduled during planned outages rather than forced shutdowns. Additionally, alarm limits support standardization and consistency across plants and sites, ensuring that machine condition is evaluated using objective and repeatable criteria rather than subjective judgment. Properly set alarm limits therefore form a critical link between condition monitoring data and maintenance decision-making. This slide introduces ISO 10816 as the primary reference standard used in this presentation. ISO 10816 is an international standard that defines guidelines for evaluating mechanical vibration of rotating machines when measured on non-rotating parts, such as bearing housings. The standard applies to a wide range of industrial machinery, including electric motors, pumps, fans, and compressors, typically operating between 10 Hz and 1000 Hz. One of the key strengths of ISO 10816 is that it categorizes machines based on size, power rating, and foundation type, recognizing that acceptable vibration levels vary significantly between different machine classes. The standard defines vibration severity zones labeled A through D, which represent increasing levels of vibration and associated risk. These zones are not fault diagnostics but rather condition indicators intended to guide operational and maintenance decisions. Engineers use ISO 10816 as a baseline reference, often supplementing it with historical data and manufacturer recommendations to refine alarm limits for specific applications. This slide explains the meaning of the four vibration severity zones defined by ISO 10816. Zone A represents vibration levels typically found in newly commissioned or overhauled machines and indicates excellent mechanical condition. Zone B corresponds to vibration levels that are acceptable for continuous long-term operation and are commonly observed in well-maintained machinery. Zone C indicates unsatisfactory vibration levels for continuous operation. Machines operating in this zone may continue running for a limited time but corrective action is recommended. Zone D represents vibration levels that are considered dangerous and likely to cause damage if operation continues. From an engineering perspective, these zones provide a common language for assessing machine condition and risk. It is important to note that the boundaries between zones are not absolute failure thresholds but guidelines based on industry experience. Engineers must therefore interpret these zones in the context of machine criticality, duty cycle, and operating environment when setting alarm limits. This slide presents the ISO 10816 severity chart referenced throughout the presentation. The chart graphically represents vibration velocity limits for different machine groups and foundation types, divided into severity zones A through D. The vertical axis typically represents vibration velocity in mm/s/RMS, while the horizontal segmentation reflects machine classification. Color coding or banding is often used to clearly distinguish the severity zones. This visual tool allows engineers to quickly assess machine condition by plotting measured vibration values against the appropriate machine category. Understanding how to correctly read this chart is essential for consistent alarm limit setting. Misidentifying the machine group or foundation type can lead to incorrect severity assessment. Therefore, engineers should always verify machine characteristics before applying chart-based limits. This slide provides a step-by-step engineering method for interpreting the ISO 10816 severity chart. The first step is to correctly identify the machine group based on rated power, shaft height, and machine type. The second step is to determine whether the machine is mounted on a rigid or flexible foundation, as this significantly affects acceptable vibration levels. Next, the measured overall vibration velocity is obtained from the monitoring system under normal operating conditions. This value is then compared against the chart limits for the identified machine category. The resulting zone indicates the vibration severity level. Engineers should also consider operating context, such as transient conditions during startup or load changes, which may temporarily elevate vibration. Proper interpretation ensures that alarms are based on representative operating data rather than isolated or misleading measurements. This slide focuses on translating ISO 10816 severity zones into practical alarm limits. In most industrial applications, two primary alarm levels are defined: an alert, or warning, level and a danger, or trip, level. The alert level is commonly set near the boundary between Zone B and Zone C, indicating that vibration has increased beyond normal and investigation is required. The danger level is often set near the boundary between Zone C and Zone D, signaling an unacceptable risk of damage. Engineers should not rely solely on standard limits but also consider historical baseline data, machine age, duty cycle, and criticality. For critical machines, conservative alarm settings may be justified. Alarm limits should also be reviewed periodically as machine condition, operating regime, or process requirements change. This slide presents a practical example to illustrate alarm limit setting. Consider a medium-sized electric motor driving a centrifugal pump on a flexible foundation. Vibration measurements indicate an overall velocity of 4.2 mm per second RMS, based on the ISO 10816 chart for this machine category. This value falls within Zone C. An engineer would typically set an alert alarm slightly below this level, for example at 3.5 mm per second RMS, to provide early warning. A danger alarm might be set at 6.0 mm per second RMS, approaching Zone D. Trend analysis would be used to assess whether vibration is stable or increasing. This example demonstrates how standards, measurements, and engineering judgment combine to form an effective alarm strategy. This slide highlights common engineering mistakes in vibration alarm implementation. One frequent error is applying generic alarm values across all machines without considering size, foundation, or duty. Another mistake is ignoring long-term trends and reacting to short-term spikes caused by transient operating conditions. Failing to update alarm limits after major maintenance or process changes can also lead to misleading alarms. Additionally, over-reliance on overall vibration levels without complementary spectral analysis may result in missed fault diagnosis. Awareness of these pitfalls helps engineers design more robust and reliable vibration monitoring systems that support informed maintenance decisions rather than reactive responses. This concluding slide summarizes the key messages of the presentation. ISO 10816 provides a well-established framework for evaluating vibration severity and setting alarm limits for rotating machinery. The severity zones offer guidance on acceptable, unsatisfactory, and dangerous vibration levels but must be applied with engineering judgment. Correct identification of machine category and foundation type is essential for accurate interpretation. Alarm limits should support early fault detection, maintenance planning, and equipment protection without causing unnecessary interruptions. By combining international standards, plant-specific data, and professional engineering practice, organizations can implement effective vibration alarm strategies that enhance reliability, safety, and operational performance.